But what are the flaws to this? There are clearly flaws which we're kind of starting to talk about, but there are real fundamental flaws to peak power testing using cycloergometry, particularly using the Wingate test. We've just talked about the older versions of the ergometer. This is nice because this gives us limited resolution. In other words, if the ergometer is only able to sample every crank revolution, you're getting anywhere between a 6 to 12% error. But if you've got a device like a loader that can record at 1,000 samples per second, so that's irrespective of where the crank is in that cycle, then clearly the resolution is much, much higher. Therefore, the ability to estimate power is far more specific. We then get to this thing of load correction. How do you apply the load? So in other words, in the test, what generally happens is you've got a resistance which is on the flywheel and you pedal against it. So think about this very logically. If I start with the resistance already applied and you have to accelerate against it, you've got to overcome inertia. So actually a lot of energy is lost in just accelerating the pedals. So what about other ways? Well, one of the ways is that we just simply hold the weight up, the participant accelerates, when they're at peak cadence, what we think is peak cadence, we just drop the weight on. But you've got the same issue. For them to accelerate, they're using energy, stored energy, which we're not now measuring. So what about if the participant drops it? So we have on our ergometers a trigger which allows the participant to drop the resistance of their own accord. Same thing applies though. One, until they drop it, they're using the energy that instantaneous energy. And two, if we're talking about test retest reliability, there's going to be variability in when they press that trigger, as there would be in terms of us dropping the weights on. Or maybe the option is to apply the load in terms of applying the load in terms of using the cadence. So perhaps we get to the point of peak cadence or 120 revs and it drops on. So this is all to do with the load application process, which is the bottom point. Load correction is somewhat different. Load correction is this notion of why is it 7.5% body mass? Because if you've got two individuals of similar body mass, two individuals of similar age, and one's 110 kilos and one is 70 kilos, there are significant differences in the amount of resistance they've got to work against. So one of the criticisms is that the original protocols never used what's called a load correction. And a load correction is actually a fairly simple process that you work out prior to the test what is the optimal combination of what is the optimal combination of resistance, that is the load, and acceleration. It's what's called force velocity. High force, low velocity. Low force, high velocity. Somewhere in the middle is a sweet spot, which is power, the highest power output. So maybe identifying that before the individual starts the test is important. And then we've already referred to this, which is the loss of instantaneous power. You have to accelerate. So you lose all that power from the high energy phosphates, probably without ever assessing it. Either because you haven't got significant resolution on the ergometer, or because the resistance hasn't been applied to the flywheel because you're asking the participant to get up to an optimal cadence. Well, if we come back to this from Ralph Benneker, so Ralph writes this: the results underline the fact that the Wingate anaerobic metabolism is highly anaerobic and show that 80% of the energy turnover during the Wingate test is derived from anaerobic, alactic and lactic metabolism. So 20% is coming from aerobic metabolism. And in fact, actually, if you look inside the paper, although he's writing here it's about 80%, one of the estimations they make on the different models was that 27% was coming from aerobic sources. So it's not necessarily affecting our power score, but it is probably affecting our, if we're using the Wingate test for anything other than power. I've mentioned the idea of using braking forces and correcting. I just want to show you this because this is quite interesting. So what you've got here is the y-axis is the peak 5-second power, and the x-axis are different braking forces. So rather than using 0.75 newtons per kilogram, or so this is in newtons, they've used different braking forces. So what they've in essence done is they've estimated this force-velocity relationship. And it's really interesting because imagine going to the gym, just to put it into context, and you put a heavy load on the bar. To move a heavy load, it goes really slowly, it's really hard. And you may not even move it, but it's really slow. You put a light load on, bang, okay, it moves. Power is the function of, is really a function of how quickly you can move that load. So what we are looking for, if we're trying to measure power optimally, we're looking for your individual association between load and time. So what they've done here is in a series of pre-tests, what they've looked for is that optimal combination. And so what it's showing us actually is that in this example here, both our anaerobically, in fact in all of our groups really, it was at 1.05 newtons per kilogram of body mass. And you can see what the effect is. That's not probably the optimal one because there'll be a point actually where it drops off. They haven't taken it far enough. But you can see clearly a difference between aerobically and anaerobically trained. Anaerobically trained produce more power. But the relationship that you will get in terms of the power is an inverted U. Whereas the force velocity curve is an exponential. So the two go hand in hand with each other. And so this is the idea of trying to find a load corrected resistance, which using a fixed resistance doesn't take into account and therefore offers higher degrees of variability in the data. So here you can see this in real action. So this is from Dave Jones's group. And what you've got is optimized versus corrected power. So you've got the corrected using filled and optimized using the non-filled. Slightly different ways, but if we just follow the notions of these, what you can see is that they've gone up from 5% to 6 to 8 to 9 to 11%. Now, if you look at the corrected, which are the filled ones, and you look at the peak power on the right hand panel, which is in our males, you'll see that at 9.5% you reach the peak power and then it drops off at 11%. Much higher than the estimated 7.5%. And in the females, actually the peak power was reached at an 8.5% corrected score. Showing us that using a fixed resistance is not appropriate. You have to load correct or load optimize. Coupled with that is this idea of what happens if how we apply the resistance. So this is the idea of a starting cadence. So we've talked about this idea of using the loader and then having the resistance drop on based upon the participant hitting a particular cadence. What I want you to look at is the top panel. So here we've got the notion of going from stationary. So this is basically the resistance is there, 3, 2, 1, and you just start to accelerate. Look at the scores for power output in watts. Okay, so in the uncorrected method, just look at the uncorrected method for the moment. So that's using a fixed resistance. So it's about 1,000 watts for males, 635 for females. Look what happens though as soon as you adjust and say, well, the resistance will be dropped at a particular cadence. It comes down when we go at 60 revs per minute, but it's higher when we actually go to 120 revs per minute, because it's that issue of overcoming inertia. If we then look to the time to peak power, which is in the larger table at the bottom, stationary it's about 4.4 seconds. Sorry, 4.84 seconds. Look at it when it's high, 0.92 seconds. 0.92. And also notice the variability has come down. So actually, one of the things that's been advocated here is just, one of the options is just to allow this to start at a high revs. Now the issue is, what do you class as high revs? So we know that in kind of relatively well-trained individuals, 120 revs per minute is pretty close to where most people are going to top out during this kind of test. If you go for track cyclists, you're looking at 150. So you have to again adjust the protocol according to the group that you're working with. Here you've got the effects of seating and standing position. Doesn't matter kind of which graph you look at, but you've got peak on the left and you've got mean on the right. And you can see standing is in the black, seated is in the white. And of course, what it's showing you is, well, actually, if they go for standing, on the whole, they are, particularly if we take kind of the mean, they're higher. They are fairly close if we go for peak power. But what you'll see is the error bars are also both showing high degrees of variability. The point that's been raised and came really from this study by McClester was, by having people standing, it opens up more variability into the study. Because when do you allow them to stand? Do you allow them to stand for the whole test? If they stand on the pedals for the whole test, how much do they stand on the whole pedals? Are they fully standing? Are they at a particular kind of knee angle for the standing? Remember that what we're trying to remove is ambiguity in the data. That's kind of the message that's been coming out across all of these sessions. Take the ambiguity out of the data. Get them seated. Here you can just see optimized loads, different ergometers. So you can see just the effects this is in boys and girls. And you can just see the effect. You've got a Fleisch versus a Monarch. And you can actually see it's slightly different calculations. Don't worry about kind of the units. But what we know is that actually different ergometers do affect the outcome of the test. So one of the other things you've got to think about is you can't interchange ergometers. You've got to stay with the same make and model of ergometer. And in fact, actually, for absolute consistency, the same ergometer in your laboratory. So what do we conclude from this? No significant difference in peak power output or mean power output was observed across 4 trials of a 6 or 30-second WIngate test in physically active males and females, indicating that familiarization may not be required to establish a consistent performance. So that's really good. So what it's saying is, look, actually, as much as there's inherent problems with this, test retest is quite good if you're interested in that kind of 6 seconds of the test. So if you're interested in the power, then actually doing a 6-second test looks like it's fairly reliable. So let's just show you this. This is kind of a 10-second example. Just show you this. So here you can see the resistance that's on the bike. Participants pedaling against the resistance as hard as they possibly can. And then the PC is picking up every time the flywheel goes through. There's a photoelectric cell recording the spinning of that. Well, sorry, a magnetic cell recording the spinning of the flywheel. And I wanted to show you this because Simonu proposed basically a variation of the WIngate test, which was a 10-second variation of this. And in the 10-second variation, nothing gets different. Everything else is the same as was proposed for the WIngate test, but it's 10 seconds rather than going for the full 30 seconds. The only difference, I suppose, really is it's 10 seconds and they suggest we'll do it twice for reliability. But actually what we've just shown is you don't need to do it twice, because the data is suggesting to us in a WIngate test, which is 30 seconds, that the first 6 seconds is highly consistent. Again, fixed resistance, same things apply. You're recording the power output to the highest resolution that you've got from your cycle ergometer. So it may be, although Simonu was onto something, actually quite simply, just shorten the test. If all you're interested in peak power output, 6-second test. Remember, by 6 seconds, the PCR concentration across almost everybody has declined enough that glycolysis is kicking in. So if you're only interested in the peak power, just use a 6-second test.